Hello and welcome to Forward. Our guest today is Casper Wilstrup, the CEO and founder of Abzu. Abzu was born in 2018 in Barcelona and Copenhagen, when 7 co-founders set out to challenge the paradigm of traditional black box AI. Today, Abzu has customers among the top 10 pharmaceutical companies, biotech enterprises, and academic institutions. Casper is an AI researcher with 25 years of experience building high-performance systems for data processing, analysis, and AI. At Abzu, Casper applies his passion for advanced data analysis and adaptive systems to achieve his dream of revolutionizing artificial intelligence. In this episode, we discuss Abzu's ability to address use cases generally considered unsuitable for modern AI, where data is scarce or causality must be established. We also talk about their work with life science and healthcare organizations, how to teach the machine System 1 and System 2 thinking, and Abzu's path to general artificial intelligence. Casper, welcome to the show.
Thank you, Artem. Very nice to be here.
The AI system you are building at Abzu is unlike any other system we hear about these days, like GPT-3 or Palm or Stable Diffusion. What do you see as the main shortcomings of these modern machine learning systems that led you to start working on Abzu?
Shortcomings is maybe too strong of a word. I think most of the technologies out there are all based on deep learning, the concept of deep learning and neural networks, and have some unique properties that are very promising and useful in certain contexts. But it also has limitations or situations where it's not the most appropriate way of doing machine learning, or maybe I should even start using the term machine reasoning. And that has to do with what it was designed for. Neural networks are designed to be as predictive as possible given a set of data. It can find arbitrarily complex interactions in that data and very accurately predict what will happen or properties of that data set based on the data itself. And for that, it's very powerful. It has a few disadvantages, one being that neural networks are very data hungry. But the other, and maybe the main advantage that motivated me to do what we're doing here at Abzu, is that deep learning models are just not designed to be particularly explainable. And they are designed with prediction in mind, and they're good at that if you have sufficient data, but they're not good at giving reasons for why they came up with the predictions they came up with.
How do you see the reasons for that in terms of the technical implementation of those systems? Is it intrinsic reason that cannot be overcome? Or is it just us not being yet able to develop that quality?
It's fundamentally an intrinsic reason that cannot be overcome. But you can go a long way with different types of machine interpretation approaches, what some people call explainable AI, to try to tease out the underlying structures in the behavior of a deep learning network. So you can mitigate the problem by applying a lot of different algorithms. The machine learning listeners in the audience will have heard about SHAP and LIME and approaches like that can actually go some way in explaining the behavior of an otherwise black box machine learning model, like a neural network. But at the end of the day, you are explaining a behavior that is learned and which is arbitrarily complex. So you're not ever getting to the bottom of what the machine learning system actually does if it's based on deep learning. So again, the answer is yes and no. There's something intrinsic in the way that the deep learning is designed that will make it forever a little opaque how it arrives at the predictions or decisions it arrives at. But we can do various things to get closer to understanding it, and that's valid in its own right. But I think there is another way, and that is to, at least for the kinds of situations where you don't really need a deep learning network, where you can go more directly for the explanation in the data and bypass the entire problem. And sometimes, I guess some listeners will have heard about Daniel Kahneman and his book Thinking Fast and Slow, which is a very popular book. And there's a lot of interesting stuff in that book. But one of the things that's a metaphor carried out throughout the book is the idea of System 1 and System 2 being two modes of reasoning in the human brain. And System 1 is fast, intuitive decisions. It's like when I see a picture of a bus, I immediately know it's a bus. It doesn't really take any conscious processing for me to realize that here I'm looking at a bus. And that's what a neural network is like. Right? It's really good at coming up with decisions based on large input data sets, like in this case, a very complicated picture and identifying a bus in that picture. But that's a system one style analysis that happens in the human brain. But we also have another mode of operating, a mode where we switch into thinking mode. Actually, most neuroscientists think that this resides in our neocortex, where we can really think about how things fit together from a logical or causal point of view. So if I say, for instance, how many red cars are there in California, then quite likely you will activate your system 2 in your brain, and you'll start to think, how many people are in California, and how many of those have cars, and what fraction of those cars are red, and then you'll arrive at some answer. But the interesting thing here is how different is that from how you recognize a bus in a picture. One is a fast, intuitive, data-driven, almost inborn ability that the human brain has. And the other is a learned thing that we can practice. We can become better at reasoning, and it requires energy and to a certain degree also willpower to reason through it. And Daniel Kahneman refers to these two ways of thinking as system 1 and system 2. If you think about that in the context of artificial intelligence, it's very clear that deep learning is a system 1 approach. It does exactly that, and it does it very well. Just like the human visual cortex does that exactly very well for object recognition. So it shouldn't be a surprise that deep learning also turns out to be the best technology for quickly identifying objects in pictures, for finding patterns in unstructured audio data, for instance, and sequences of data, where it's like a learned, intuitive, quick decision that takes place. But it will forever be difficult to really explain how a system 1 arrives at its decision. So that's why a system 2 style approach is also useful in artificial intelligence. And I guess that's one way of phrasing what we set out to do in Abzu. It was to build an AI that is purely and clearly a system 2 style reasoning approach.
This is a very good framing of what you're working on. And interestingly, Kahneman talks also about how you can use, in that example of the cars in California, how you can use System 1 to try to estimate the number of cars. You'll get the wrong answer, but you might still be sure that the answer is good, because System 1 can hallucinate just like our neural networks can and give you a completely wrong answer, and still you will be convinced it's a good one. And he actually warns about not using or not relying on System 1 as much as we do in our daily lives and in our decision making. I think everyone who wants to understand neural networks capabilities today, using the book, Kahneman's book, as a guide is a good idea.
Yes. And actually, Kahneman even takes a step further in his analogy. I'm not sure if he thinks about it this way himself, but a very clear guiding thought throughout the book is that you can activate System 2 on demand. It's a limited resource, but you can actually activate it. And it can then go in and re-examine the decisions made by System 1 and justify it. This is where Kahneman gets very interested in how it more behaves like a lawyer than an explainer. But nonetheless, the idea of System 2 being activated to check out the conclusions of System 1 is a very important idea. And I think if you think about it in the context of the bus recognition example before, if you close your eyes and quickly imagine seeing a bus, then right, you'll be able to recreate what does a bus look like. So that's an experience that's fairly easy for us to recreate. But it's interesting to say, even if it's an imagined bus, then if I ask you, how did you know that what you just imagined was a bus? Then you don't phrase it in terms of anything that has anything to do with the picture. You start justifying your decisions based on the fact that it is long and square and has wheels and has windows and have all the properties that we come to be familiar with in a bus. But actually, well, you most likely didn't see that when you saw the bus, right? So it's an afterthought. When somebody asks you, why is this a bus? Then you start justifying your claim that it's a bus based on things that you didn't actually see before deciding it was a bus. And it even works with a mental picture of a bus. Even if you didn't imagine the windows when you were imagining the bus, you'll still say that that's part of the reason you think that what you were imagining was a bus. So this is an interesting property of the human mind, that we can actually introspect so strongly on the behavior of system one. And if you look at the way the brain is structured, that's not really surprising. Like the neocortex is wrapped around the entire older parts of the brain and reaches into the inner parts of the brain and actually has access to a lot of the working there. So maybe, and this is me speculating about how our brains evolved to be exactly the way they are, but maybe that's exactly the point. The neocortex is a high energy consuming, limited resource that is able to go in and analyze the behavior of a more original primitive brain that we inherited from our forebears. One way of thinking about the state of AI today is that we have run forward with the ideas of system one, and I think we've become fairly good at mimicking that in a lot of the research into neural networks, but we're lacking sorely in developing a system two to go in conjunction with the system one in our AI approaches.
The way I see it is quite similar to what you just said. I have these modules of our mind that I call intuitive estimator, then imaginator or dreamer, then muscle memory, and then reasoning and logical thinking. And we started with the intuitive estimator, the first neural networks. Some call them predictors, but to predict kind of implies you can look into the future somehow, but they don't. They just estimate based on the past data. Then we moved to the muscle memory types of things, like the things that can keep your car within a lane based on pure visual data stream, or can control plasma in fusion reactors. All those things that we can train the systems to do automatically, like we train ourselves. And then we went to dreamers like GPT-3 or DALI or Stable Diffusion, where we can come up with text, coherent texts or coherent pictures that won't be perfect because the reasoning piece is lacking. So the horse may have 5 legs instead of 4 and all other issues, but they will be quite impressive. And now the next important piece is the logical reasoning, the thing that you work on. So let's talk about Culattis. It is a symbolic regressor as far as I understand. What is symbolic regression and how does Culattis address these issues of the ML models that we talked about?
The Culattis is currently used mainly for symbolic regression, but at its core, it's actually not a symbolic regressor. At its core, it's a graph finding algorithm. And a graph finding algorithm, here I mean the word graph in the computer science sense of the word. So a graph is a thing that has nodes and edges. So if you think about relating some property, let's be a little mathematical and say that you're relating y to x1 and x2, then there's various ways you can do that. You can take x1 and then you can connect it with an add node, and then you can take x2 and connect it to the same add node, and then you connect that output to y. Then you have a graph where x1 and x2 are at the initial nodes, and the plus is at is a node in itself that the other two are connected to, and so on. If you can imagine such a graph in your head, it's like a little two-legged fork with y at the end, and the x1 and x2 at the two legs. That kind of thing is what a computer scientist would call a graph. And they can be arbitrarily complex. They can be much bigger than that with nodes and edges all over the place. And in a way, almost everything that we come across in terms of flow diagrams, decision trees, mathematical expressions, so on, can be written out as a graph. So in being able to find graphs, we can solve problems from finding mathematical expressions to finding logical flow diagrams to finding Bayesian networks and so on. All the kinds of things that you would be able to write out of as a graph can be found using a graph finding algorithm. Now, the problem with graph finding algorithms is that if you have a set of starting points and you're looking for the best graph to get to another point, the end point, then there's an infinite set of routes that you can actually take. That's the annoying thing. Some people would say that's why graph search algorithms tend to be what computer scientists would call NP hard. It's like there's no logical way to say that you've exhaustively searched through the entire space of all possible graphs that you could search. This has been tackled in a range of different ways, traditionally with methods from evolutionary computing particularly something called genetic programming. But there has been other evolutionary computing approaches to try to tackle that problem unsuccessfully. And this is actually, it's as old as AI itself to try to do AI with graph searching algorithms. It's all the way back to McCarthy, actually the inventor of even the term AI back in the 50s. And that entire family of AI algorithms have been dubbed symbolic artificial intelligence. They didn't call it themselves that back then. Turing and McCarthy, they called it AI. But nowadays we tend to call that symbolic AI because it's looking for graphs that can be symbolically represented to explain how things relate to each other. Now, the idea of symbolic AI kind of went south with the second AI winter. It didn't actually quite work. And then deep learning showed up, neural networks, as we called them at the time, before they were rebranded. And it turned out to work very well. And then neural networks, in a way, squeezed the idea of symbolic AI in the background. This happened back in 89, 90, 91, 92, actually, when I was a fairly young physics student. And since then, we've kind of given up on symbolic artificial intelligence and focused exclusively on deep learning. The technical term for deep learning and similar approaches is actually sub-symbolic artificial intelligence. And I guess today, most researchers who know these terms would say sub-symbolic artificial intelligence 1. But I would say sub-symbolic artificial intelligence is system 1. You're never going to solve system 2 style problems with a system 1 style approach. So in order to revisit this problem, we have to look at symbolic artificial intelligence again. And symbolic artificial intelligence is, as I said, very well phrased as graph searching algorithms. They're just hard because you're searching through these annoying infinite spaces. So the Q lattice, which is the algorithm that we have invented here at Abzu, is essentially an algorithm that uses some tricks that were developed to study quantum fields, which is something I worked with a long time ago, to search these infinite spaces of possible graphs and come up with the graphs that match a certain criteria after looking through an infinite set of possible graphs. So it's all very intricate. How can you actually look through an infinite space? And maybe we'll get to talk more about that. But the outcome essentially is that you get the graphs out that are the best fits the question you ask. So I think you could say that we here at Abzu have solved that problem. We've found the missing piece to make symbolic artificial intelligence work. Now, symbolic artificial intelligence and symbolic regression isn't exactly the same. Symbolic regression is about finding graphs that are at the same time also mathematical expressions. So currently, we here at Abzu are using the Q lattice for symbolic regression mainly. And if you use the freely available version of our package, which you can find on PyPy if you search for Q lattice, then you'll get the symbolic regressor. But there's much more to it, and we have much bigger plans to use it for other graph search problems in the future.
Okay, so we definitely should talk about both parts, starting with the part that currently available to your users and customers, the symbolic regression and ability to find the right formula to approximate the data that the user has. Talk about how it works, what kind of benefits it gives to the potential user, and what kind of data it needs.
Starting with the benefit and then the data, and then we can, particularly if you remind me, we can return to how it works in the end. But the benefit. So analogy that actually isn't mine, it's one of my colleagues, Mira, who came up with this analogy, is Kepler's law of planetary motion. So there once was a Danish astronomer called Tycho Brahe who sat on an island in Øresund here, the water that I'm actually looking at if I look out the window, and he was studying the orbits of Mars. So if you take, and he wrote down very clearly how does Mars traverse the sky. And if you take that data and you put it into a neural network, you will get a model that can accurately predict where Mars will be on Earth's sky at any point in time in the future. Right? There's sufficient data to train a good neural network on it, so you can actually predict where will Mars be on the heavens on a given day with a fair accuracy. Now, if you just want to know where Mars is, then all good. Right? That's what you needed. You don't care about why Mars is there and why it moves the way it does. But if you instead take the same data and put it into the Q-lattice, what comes out is a formula. And that formula expresses the location of Mars as a ellipsoidal mathematical equation. And this ellipsoidal mathematical equation is actually what we nowadays know as Kepler's law of planetary motion. It is this elegant rule that says that planets move in ellipses, and the sun is in one of the foci of the ellipses, and the rate of motion is also spelled out by actually Kepler's second law. So this is a parametric formula that describes the motion of Mars. It just so happens that it also describes the motion of every other planet or every other celestial object in the universe, because it is fundamentally governed by an even more fundamental rule, which is Newton's law of universal gravitation. But the point here is, if you care about Kepler's law, then a neural network will do nothing for you. It'll stop you blank with the predictor, and that's how far you'll get, and you won't get any further. If you care about the underlying rules governing the observations you make, then you need a system like ours. And again, if you think back in the context of System 1 and System 2, it stands to reason that you could teach, an ant to always look at where Mars will be, because it's a intuitive judgment thing that can be learned to do intuitively. But it required System 2 and a very thorough reasoning process on behalf of Johannes Kepler to actually take these observations and turn them into Kepler's laws of planetary motion. So using the Q-lattice gives you Kepler's laws, and using a neural network gives you an estimator for where Mars will be. And therein also lies the benefit. If you care about the generalizable picture, if you want to understand the underlying question of why, then you should go with a symbolic approach. And that's why the users we have today are the people who care. So there are many situations. I'm not saying that you should always care. There are many situations where it really doesn't matter. You just want to predict. But there are more situations than you would think where you really do care about the why. Maybe you just have forgotten because you've given up on getting the why. Let's say, for instance, that you're studying your churn. You're studying customer churn at the e-commerce store. Yes, you can use various types of machine learning to very accurately predict who will churn next. And maybe that's good enough. Then you can call them and say, please don't leave my business. And that's fine. But again, if there existed a technology that was able to not tell you that people would churn, but why they churned, the reason they're churning is because they are waiting for more than 3 hours in support calls or some other reason, then I think most people would prefer that. So there's always an added benefit in the why, I would say. But the importance of why scales from almost irrelevant to the most crucial thing of all, depending on the actual use case. So our users tend to be towards the case where they care more about the why than the what. And that's the benefit. In terms of data and the data needed, the answer is a little complicated. Actually, so neural networks are very wasteful with data. The Q-lattice always works a lot better than neural networks with the same amount of data if there is an underlying causal explanation to be found in the data. But that's because neural networks are actually probably pretty much the poorest example of a machine learning technique if you don't have huge amounts of data available. There are other machine learning techniques that are better fitted for less data, like random forest approaches or various kinds of ensemble estimators, gradient boosting, and even Bayesian networks or self-inferred Bayesian networks. There are approaches that works reasonably well with small amounts of data than deep learning does. The Q-lattice scales interestingly with the amount of data available, because the Q-lattice itself, being a graph search algorithm, will just give you the statistically most likely explanation present in the data. So if you've collected data about 18 patients, we have customers who have data about the full gene sequencing of 18 patients with a rare disease. And if you just have 18 patients, there are limits to what you can statistically infer from that data set. And the Q-lattice will comply with those limits. So it will tell you that in this model, I can only say that it seems to be this gene and not this gene that could be supported by the data with a certain probability. And that means that the Q-lattice works well, even at, say, 18 data points in this case. But of course, it cannot then find very complicated relationships because they are not statistically supported in the data set. As more and more data becomes available, the Q-lattice can find more and more hidden, more and more complex nonlinear interactions in the dataset until, in the limit of infinite data, it approaches the same behavior as a neural network. If you let the Q-lattice run wild and says, just give me the most arbitrarily complex equation you can find, given this huge data set of millions of observations, then what comes out actually will look a little bit like a neural network, because a neural network is also a very large mathematical expression in its own right. So the point here is that the Q-lattice, in that it complies with the rules of statistics, will work for arbitrarily small data sets, but it will give you arbitrarily, thereby it will necessarily give you simpler and simpler explanations because they need to be supported by the actual data it was shown.
Usually symbolic regression tries to find the simplest formula that would approximate the data. Is that the case for Q-lattice?
When I say it finds a graph that matches the criteria that we ask it to. So if we ask it to, if we define what we mean by simplicity, then it will find the model that is simplest. But simple is a hard concept to define. The way we deal with it is we define it in terms of statistical likelihood. So the default behavior for our symbolic regressor is to sort the graphs and thereby the formula that it returns by how statistically likely they are to not be spurious. The risk is always that if you make an arbitrarily complex equation, you can match anything. Right? Generate a large random sequence of data and find a function that can translate that into another arbitrarily random generated sequence. That's always possible if you allow the equation to be arbitrarily complex. But the complexity also spells out the number of degrees of freedom in the model, and thereby you can use it to estimate the probability that this is in itself spurious. That's what's called the archaic information criterion in statistics. There's another one, an adapted one called the Bayesian information criterion, and it's debated which one is correct. We support both. So the default behavior for the freely available version of the Q-lattice is to use archaic information criterion in the sorting, which means that you just get the models that are statistically most likely. And that means that the more data you have, the more complex the models can be while still retaining the property of being the statistical most likely model. I would like to say, though, that one of the things that most of our users appreciate the most, actually, about the Q-lattice is not really the model it gives, but the fact that it gives you an infinite list of models. Because the way you could think about this is that there's an infinite set of possible formula equations you could try out. And you can think about that as being the input to the Q-lattice, and the output is a sorted list, is this same list now sorted by statistical probability. So item number 1 is going to be the most likely one. Item number 2 is probably going to be almost as likely. The difference is most likely very marginal. So in the hands of a researcher who can interpret these formula that gets shown to him or her, it allows the researcher to incorporate the hypothesis or the models that get shown with their own prior knowledge of how the system works. So quite often the users we work with, or our customers, will actually not take the most likely model. They'll take this number 7 or the 23rd likely model because they already know this model is likely for some other reason, being that this gene that it says impacts the growth of the tumor is known to also impact other growth of tumors or things like that. So in that sense, the Q-lattice doesn't chop off the ability of the user to think for themselves. I've spoken with another journalist once who compared it to a thinking hat, and I like that metaphor, where the Q-lattice not so much give you an answer, it augments your own ability to find answers by showing you what could be true and then allowing you to decide which of these things to explore further.
Yeah, this is definitely a very powerful property when you go from not having any formula at all, and just looking at data, and maybe if you use neural network and it gave you some way to predict something based on that data or estimate something based on that data. And now you have multiple formulas that you can compare, and based on your previous experience on other data that may be not available to Q-lattice, pick a few hypotheses and work with them. Seems very interesting. And it also seems like Q-lattice is it fair to say that it repeats our scientific progress? Newton has less data than Einstein had. So Newton equations were more rough approximation of the law of the universe than the Einsteins.
Yeah, I like the metaphor, and I think it's also quite true. I have to add though that actually Einstein's special theory of relativity is, from a mathematical standpoint, actually simpler than Newton's three laws of motion. But but that's a little detail. They're just really weird. But actually, the equation itself, the one over the square root of v square, 1 plus v squared over c squared. That's the Lorentz contraction factor. It has 1 degree of freedom. That's v squared. But anyway, that is true. We work mostly with disease mechanisms and disease etiology, understanding how diseases arise and how they evolve, and also with the pharmaceutical companies at modeling how you can then produce some molecules that will prevent this process. So that's kind of our business domain. So if you think about etiology or how diseases arise, it's actually a very, what a statistician might call a degenerate problem, meaning that if you look at a thing like, let's say, breast tumor, a disease that we've studied a lot, breast tumor isn't one thing. There's like a lot of different unfortunate combinations of genes that can radically increase the probability of developing a breast tumor. And if we take a data set, let's say at a case that we ran with 700 women with breast tumor, then there are some explanations that jumps out the moment you put them through the QLASs. Right? So 60% of the women can very accurately be, their occurrence of breast cancer can very accurately be predicted by the property of them having two specific genes in an unfortunate combination. In this specific case, the combination was not linear, so it had never been found before, because barring the QLASs, pretty much the only thing you can do with this kind of data set is linear regression. But this was not linear. It's like a hotspot. Unfortunate levels of these two interacting in a bad way that created this rapid tumor growth that accelerated the body's own repair mechanisms. So that explained about 65% of the tumor growth cases. But the other explanations that for the remaining is probably more complicated than that. It probably involves 3 or 4 or 5 genes, and therefore it cannot be found in this data set. So if we collect more data, we can find the additional explanations and piece by piece say, all right, this is one etiological mechanism. This is how the disease develops in some women, and this is how it develops in the remainder, but smaller part of women, and so on and so on. And the more data we get, the more we can divide and conquer the problem until only the rarest occurrences of breast cancer remain unexplained.
And since the result is always a formula, it is perfectly generalizable.
Our results are always perfectly generalizable, with a little caveat that the parameters, the weights themselves in the formula, can change from population group to population group. So that things like if you measured it with one instrument, then if it was all measured with the same instrument, then the parameters of the model will adapt to that instrument. And then if you take a different population and measure the gene expression levels, say, with a slightly different approach, then the formula would still be valid, except for the constants in the formula. The parameters of the formula would have to be updated. But the topology, that is the shape of the formula itself, is perfectly generalizable from population to population. And here I don't mean population in the human sense, but from samples of observational data.
Would it be fair to say that the most valid use cases for QLATs at this point are the use cases where you first need this causal reasoning, need to discover causality, and where you don't necessarily have vast amounts of data used by neural networks?
Yeah, I'd love to say that you should always use the QLATs unless you have computer vision or natural language processing. One of the cases where system one is clearly a better fit. But in actuality, yes. When we look at where to go with our technology, we look for two things: data scarcity and the need for why. So if you are low on data and have a high need for why, you will probably not be using AI now at all, because you can't. So in those situations, we are the solution that the only solution available, really. And then as data amounts increases, then other options start to appear. First with gradient boosting and random forest approaches, then with designed Bayesian networks and other approaches. And then ultimately, when you hit very high data amounts, then you can also look at neural networks. So yes, it's fair to say that the situations we go for is data scarcity and a high need for why.
How does it work on the technical level? You talk about it being inspired by quantum field theory, and there is a history of different approaches to regression, including the regression that is currently being driven by neural networks.
Yes. The inspired by quantum field theory. First of all, sometimes people mix us up with quantum computing. And let me just start with saying what we're doing has nothing to do with quantum computing. But, and this is a little but that makes it a little blurry anyway, the algorithm we have would actually run instantaneously if we had a very big quantum computer. So when I say that, it's both true and false, right? Our algorithm, since it's a quantum algorithm in its own right, it's actually one of the algorithms that would benefit the most from a quantum computer of a scale of any size once those exists. So that's one interesting thing, but it actually doesn't matter to our current situation because we're talking about 4,000 qubit machines or something like that. Won't happen anytime soon. So park quantum computing. So quantum field theory. I think my younger brother is a Star Trek fan. He often uses an example of there's an episode in Star Trek where the USS Enterprise gets duplicated in millions and millions of copies of itself because they run into some kind of quantum singularity thingy thing. You know, this techno babble, the Star Trek style. But there is something interesting here, which is the billions and billions of USS Enterprises. Because the way quantum reality actually works is that when something happens, it's a sum of an infinite set of things that actually could have happened in a certain sense. So when a particle moves from a point A in space to a point B in space, we think of it as moving in a straight line. That's the macrophysical approximation. But actually, it doesn't. And here I'm not just saying it's not just a mathematical trick. I'm a believer in quantum reality in the sense that what actually happens at the reality level is that the particle takes an infinite set of different trajectories through space to go from A to B. And actually, all the trajectories it takes is all possible trajectories. So it can go 1,000 miles away to the north and then down and then 1,000 miles and then back up and whatever, arbitrary shapes. And the way to compute the probability of it actually going from A to B is to add up all these trajectories. It just so happens that as you start listing up these trajectories, they cancel each other out. Like, so there's a trajectory that goes in an upbound curve from A to B, and there's an equivalent one that goes in a downbound curve from A to B. Those two trajectories cancel each other out. That's why we end up with summing this to arrive at a straight line. This is a mathematical formalism in quantum theory that's called the Feynman path integral. It's one way of thinking about quantum theory. Gives the same result as if you solve the same thing with a Schrödinger equation. So they're completely equivalent. But I like the Feynman path formulation. Particularly like the Feynman path formulation because it allows us to solve a problem that other approaches in quantum theory doesn't, which is the quantum field theory situation, where you have a large set of particles that go around among each other and interact and arrive at some point. In that case, maybe you can even see it if you say you have 10 particles that sit somewhere in space and you start adding up all the ways that these particles can move. A lot of those paths will involve the particles meeting at some point. That's called an interaction. They meet somehow and do something together, and then that's an additional path. So if you think about that, you're already starting to see how these are graphs. The trajectories that the particles take in this infinite space of all possible trajectories are actually in themselves graphs. And what you're looking for is how they arrive at all the graphs that arrive at a certain point in space-time, to use a somewhat weird word, but they arrive at some point B at some point. So you're looking at all paths that go from say, A and B to C. That's an infinite set. In quantum field theory, that is impossible to solve analytically, meaning we can't just sit down and calculate and come up with a solution to how would this field look. So since the early 90s, actually, a method has been developed called quantum lattice gauge simulations, where you, inside of a computer, you chop up space and time in squares. It's a four-dimensional space-time square thing, so it's not quite a lattice in the normal sense, but it is a lattice nonetheless. And then you calculate all possible trajectories where the particles move from center to center in these lattice squares. And that suddenly isn't an infinite space anymore. It's very large, but it isn't infinite. So now you can make your way to the end on a supercomputer. So I've been fiddling with that in the 90s as a physics student. So this is where my experience with this approach comes from. I was very involved, particularly in high performance computing systems back then. And then you make the lattice size smaller and smaller, and then you see if the probabilities of arriving at point B converges to something. So you're testing convergence as you make the lattice grid more and more fine grained. And the biggest supercomputers in the world are actually built with this specific thing in mind to solve a problem in something called lattice chromodynamics, which has something to do with quarks. Not important for this discussion. But anyway, maybe it's becoming a little obvious here that since we have a method that is designed to look at ever more complicated graphs in space-time, it is actually a graph search algorithm. In the quantum lattice gate simulation situation, you add up all the graphs. We don't have to add up all the graphs. We don't care about that. We just study the graphs in isolation. But we use the same tricks and tools that was developed to do this, to actually analyze ever more complicated graphs by making the lattice size smaller and smaller in this. In our case, it's not even a four-dimensional. It's an arbitrary dimensional lattice space. But that's why we call it the Q lattice. The Q is for the quantum lattice gate simulation. So in its current incarnation as an algorithm, you could argue that it has relatively little to do with a quantum lattice gate simulator, and you would be right. So it's more like in the inspiration of how to deal with infinite spaces of graphs comes directly from there. So that's how it works. And that sets it completely apart from the other symbolic regressor algorithms out there, genetic programming being by far the lead contender, in that it actually systematically searches through the space of all possible graphs, but it just does it cleverly by looking at them in probability order. Whereas symbolic regression with the genetic programming style relies on arbitrary recompositions and random sampling, essentially. So our algorithm isn't random. It's quite deterministic, actually. It gives you the same result whenever you run it, because it just gives you the most likely graph. And thereby we have boiled the problem down to something that's actually tractable in realistic time. Now, the Q-lattice, I keep talking about this freely available version, because the Q-lattice that we provide for free for scientific purposes, you actually have to pay if you use it for commercial purposes, is not supercomputer powerful, right? It relies on running on your own computers. That means that the lattice space is quite limited. But for simple problems, it will get good solutions. So the systems we run in-house can use our own much more powerful supercomputing resources, so we can search through huge lattice spaces and find more complicated problems, and we can find them faster. But it's fundamentally the same algorithm.
In terms of the compute needed, since you talked about systematically searching the whole space of possible graph, it does sound like you would need a lot of compute to go through that. You said you do it cleverly, so this is interesting, but maybe you can give some estimation of, for example, we're all familiar with formulas like the Kepler's law of motion. So what kind of compute power would be needed to discover that formula based on some data set?
On my laptop, the one I'm talking to you on right now, that would take 1 to 5 minutes.
Okay, so the algorithm is actually quite efficient.
Yeah, it is. But that's because Kepler's laws of planetary motion isn't that complicated.
And then if we go a step further, what would be the next level of complexity in terms of formula and in terms of compute needed?
Yeah, biological systems are the interesting example here, because biological systems are very annoyingly complicated. Like the development of a cancer or the occurrence of, I personally have worked a lot with a disease called preeclampsia, is just complicated. There's a lot of things that interact, and any formula you come up with will be inadequate, and you'll be able to make it better by adding yet another parameter. Takes things, or even there's the divide and conquer, which is two different trajectories here that you can take. But fundamentally, when you talk about biology, a lot of things interact, and it is actually still causal. So we have models where there's 10 gene expression levels or 10 serum measurements and gene expression, various omics levels. So in studying human biology, we often use the word omics, which is just a truncated works of genomics, proteomics, and so on, where there's a lot of measurements you can make on the human body at different levels of biomolecules. And all of these tend to interact in interesting ways to lead to the actual development of the organism. And in those situations, again, I had the breast cancer example before where we found a 2-gene model. That takes 10 seconds to extract from the data. But then there's the 7-gene models that are also likely to be true. And they would more like take half an hour to extract and on my laptop. And sometimes, actually, quite often, we work with molecular modeling where the things we're actually studying is typically RNA strings. We work a lot on a specific modality, a specific type of pharmaceutical medicine called RNA therapeutics, where the molecules themselves are little DNA or RNA strings. And modeling the properties of those in terms of themselves can involve 10, 20, 30 parameters. And then we're talking sometimes up to a day. And even on our powerful computers, it can take up to a day to find these models. So it scales with n cubed. Unfortunately, that's how these graph search algorithms usually are. But since it's so clever, I would like to say, for most use cases, the constant in the O of n cubed here is quite low. So you get good solutions even within a few seconds. Most of our users see this as an extremely fast system. But that's also because some of them came from deep learning, where you learn patience.
One day is nothing compared to the modern experience of setting up a deep learning system that can take you months to get to the result.
Yeah. Been there. And the iterative loop as a developer and doing a deep learning model is just enough to make you want to do Q-lattices instead.
And then you discover that there is a bunch of issues with your data that renders all the work that you've done less applicable than you expected it to be.
Or you have a sneaking suspicion that some little change would have given you a different result, but in order to check it out, you have to set aside another week. So you just decide to ignore that.
How is Q-lattice used in the real world right now? You talked about 2 groups of use cases: disease etiology and understanding drug properties.
Yes. And in terms of Abzu's actual business, that's what we do. We work with academic institutions for pro bono, actually, for disease mechanism and understanding diseases. We work with a lot of different academic groups understanding and studying different diseases. But when we get closer and closer to understanding them, where it becomes what's called target identification, we're starting to understand the etiology, how the disease develops well enough to identify possible intervention points, like reduce the level of this protein or silence this gene in a certain way. Then we get into our commercial operations, where pharmaceutical companies are quite interested in identifying new druggable targets, which are these intervention points in etiology that they can then start looking to develop medicines against. And this is something we work with a lot of different pharmaceutical companies, actually, in this interface between disease mechanism understanding and identifying the targets that can then prevent those diseases from developing or evolving. I'm personally quite involved in that. I don't have a background in medicine at all. I'm maybe clear by now. I have a more like a physics and statistics and mathematics background. But I have taken to the etiology quite strongly. It really motivates me a lot because there's something extremely fascinating and purposeful in helping understand diseases that are actually serious and makes cause of a lot of suffering. So I really like that. But so I work mostly with that. Maybe later we can talk about our style of working here at Abzu. But one thing everybody can do and should do these pro bono kind of things as part of what we do, where we go out and look for problems we can solve with the Q-lattice without necessarily getting paid. Anyway, that's where I have a lot of the insights. So here, typically the workflow is that we sit together with a research team, typically a couple of doctors and a biologist, something like that, and then we analyze and interpret the data. So it's quite fascinating. It's more like this thinking hat is actually on several people at the same time. So if you want a metaphor, maybe it's me, a medical doctor, and a biologist sitting together in a room, and then we put it on this collective thinking hat, which is the Q-lattice. And then we come up with new theories about why preeclampsia develops in women, for instance. And then we go on to devise how could we now set up an experiment to validate this hypothesis. So this is one side of our business. It's not the biggest side of our business. The biggest side of our business is once the targets are identified. We work with RNA therapeutics mainly, which is a class of drugs that is very easy to design in terms of interfering with a target. So once you know that a certain gene is the cause or partial cause of the disease, the easiest possible way you can reduce the level of that gene is to design an RNA therapeutics that is, in this case, actually the reverse transcript of the mature RNA of the gene, but that can then cancel it out kind of in the cells. So you can inject a certain kind of medicine into the body that essentially cancels out the gene as long as the medicine sits there. There's a lot of issues with RNA therapeutics. First of all, I alluded to one of them. It's not a pill. It will never be a pill. It's something you inject. Point two, it's quite unstable. It tends to not stay in the body for a long time, and maybe it doesn't make it into the cell nucleus where it should do its magic. Point three, it's very often has adverse side effects. Like if it knocks down a certain gene, it has a risk of knocking down other genes as well, and that's not what we want. So in terms of making it all the way to the market, there's a lot of challenges, but I still think it's a very promising future. But one thing that is particularly wonderful for is testing out if we were right in the target identification process, right? Because that doesn't have to be done on a human, it can be done in a cell. So once we speculate that a certain gene sits on the etiological pathway to disease, then that's really a hypothesis. And the next step is then we can design a molecule, an RNA therapeutic molecule that will cancel that gene in a cell. And then we apply it to cells, and then we can validate the hypothesis. So we can move from disease mechanism understanding, target identification, to validating that this target is indeed in the causal pathway of the disease in a manner of actually weeks, rather than the 3 or 4 years that the industry has taken previously to do the same process. Actually, it's a very forward. Today, the industry is organized, the pharmaceutical industry is organized in a way where you do this in a very stepwise forward funnel-like approach. And we're really promoting and pushing for a much more iterative approach. Collect data, identify possible targets that are now hypotheses, do an RNA therapeutic to test it in a cell line, move on if it seemed to be right to the next stage, which is then property or safety, making sure that it's actually safe and toxic, not toxic, and so on. So this is where the majority of our actually, from a financial perspective, the majority of our business is in understanding these molecular properties of RNA therapeutic medicines.
The change to approach from the waterfall, as we would call it in software, to the iterative process wasn't possible before, because every step, every stage was extremely complex and time-consuming and expensive. But now, with your technology, you expect that it is going to be much easier to do experimentation, quick experimentation and iterations there.
Yes, all the way from understanding the disease to target identification to early drug discovery, where you develop the RNA therapeutic, and to lead optimization, which is about making sure that it's not toxic and that it's stable and that it's has all the other interesting drug properties you want, and on to actually testing it out in non-human populations to see if it actually does cure the disease in those populations. Throughout that entire process, we can make it iterative and feedback learning about, okay, how did these things work step by step. So yes, you're absolutely right. Another thing is that I've worked with software development for 25 years, as pretty much always in the high performance computing or data analysis space, but with agile methods. So there's actually two pieces here. So when we work with our pharmaceutical customers, we're both preaching explainable AI or research augmentation with AI, and we're trying to teach them iterative and cross-functional teams. But the two things actually work together, right? You have to be cross-functional in order to work in this way, but you also have to have the tools that allows the learning to arise, that there's for anything for you to do in a loop. So yes, I would say though that I love our technology. It's very cool, but I think there's another reason why the pharmaceutical industry is so waterfall oriented, which has to do with the fact that RNA therapeutics isn't that old. I think when you look at the way the industry is structured, it tends to be structured around what is possible if you're doing small molecules. And small molecules is like, it's a good old fashioned, it's what all the pills we get are small molecule type drugs. And you can't really design a small molecule to very targetedly interfere with a specific druggable target in the body. You have to do that by trial and error. So people work with massive molecular screening of various types in order to solve that problem. And inherently, that's a long process. It takes months and years to actually even develop a molecule that can target the gene that you think you need to target in order to do this. So the waterfall process comes naturally from small molecule drug development, I think. And so there's three pieces working together here in the value proposition that we have to our pharmaceutical customers. Work more agile, iteratively, incorporate the learning through the research augmentation with the QLATs, and finally use RNA therapeutics to validate your hypothesis about the disease etiology, even if your ultimate goal isn't to develop an RNA therapeutic. Because once you know for sure that this gene or this protein that it gets translated into is on the causal pathway, then it's perfectly fine to use a screening approach for small molecules to screen through millions of molecules to see, can I find a small molecule that interferes with this protein? That might be a better option ultimately, because you can then deliver it as a pill. But the first part of the value chain, go with RNA therapeutics. So this is the vision that we sell to our pharma customers.
That sounds like a small scale scientific revolution in drug development to me.
Yeah.
And we can talk more about future use cases for QLATs. But before we do so, and the path to general AI ultimately, but before we do so, I do want to talk a little bit about the company culture and your people. You do have a culture that is unlike many others, I think, and your approaches are somewhat unorthodox. So I'd love you to talk about how do you think about building QLATs as a company, and what kind of people, processes, and culture are needed for Abzu to succeed.
I guess this is about me and the way I think. I think in terms of organic systems. I think in terms of interacting particles in a system. I think like that when I think quantum physics. I think like that when I think the QLATs and how it searches spaces. I think like that generally. That many things that we encounter in the real world are more like organisms than they're like machines. And I think that most organizational design since the Industrial Revolution has been modeled around the idea of the machine. Not surprising, I suppose, because the Industrial Revolution was all about machines. And there's something that if you think that machines are going to solve to build a better commercial environment, which they certainly did in the Industrial Revolution, then it's natural to also think that other things should be like machines, including companies and organizations of humans. And in some situations, a machine metaphor is also a good metaphor for an organization. Where you need a lot of rigor in the way it works, and then a machine metaphor is a good idea. You just design your organization to work in a certain way, and think of humans as cogs in a machine. Then you get a machine that is efficient and predictable and easy to understand, and it has a lot of good properties. But if you're not manufacturing stuff, then this might not be the best. And if you take this to the extreme other end of the scale, where what you're manufacturing is ideas, then it's most likely a very, very bad metaphor for how to structure the way you work. Machines don't produce innovations or QLATs. Machines don't do any innovation. They just do what they were designed to do. So from a philosophical standpoint, I don't think you can create a research organization that Abzu ultimately is if you try to model it like a machine. It's like some people do, and then you end up with horrible things where you count citations and you think of failures as bad, whereas actually they're the other half of successes. Like one cannot exist without the other. They're equally important. A lot of things that comes from the machine metaphor that spoils the research organization. So in that end of the scale, I think the only way to think about organizing yourself is much more akin to an organism. And that implies self-organization. That implies that people interact with each other and figure out how to solve what is right there before them. They have an idea or something they want to try out or a hypothesis they want to test. And there is no predetermined way to do that. So they have to be able to say, hey, Alice and Mira and Bob, I want you to work with me on this, in this way. And then we do that, and then we learn something, and then we incorporate that learning in what we do next. So any kind of fixed organizational structure is just going to prevent that. So when we founded Abzu, I was from the beginning very keen on making this a self-organizing company in that sense. So we defined a relatively limited set of rules about how we interact. If you want to stay with the metaphor, you can think about it as the immune system and the signaling pathways in an organism. These are the ways you have to interact. And we call them things like decision processes and conflict resolution processes and sensitivity boards and things like that. And those are our formalistic structures, but they're just there to allow the organization itself to take on whatever shape is relevant to the given tasks at hand. And also to make the organization learn to become better at taking on new tasks. So this is a strong design philosophy in the way we organize here at Abzu. And it has served us well. I don't think we could have invented the QLATs if we hadn't been organized like that. It's like we're now 26 people, and we've come up with a fundamentally different AI approach that for some, at least in some use cases, is on par with deep learning that probably has been the fruit of thousands of, even hundreds of thousands of researchers over more than 40 years. So that's a little mind-blowing, actually, and I actually understand. Returning to when I founded the company, people were quite skeptical, but a lot of people were, I see a dreamer. But I was vindicated. But anyway, that couldn't have been done if we thought about hierarchies and bosses and process and clocks and stopwatches for when people did what. Well, no, that just doesn't work. However, I will recognize that as an organization grow, there are pieces of the organization that needs to be more machine-like. And our organization will go through the same process. I've been involved in other startup companies as well. I was in a startup company where I also applied this approach, where we ended up having more than 100 people in the part of the organization that worked in this way. And it scaled in a complicated way, particularly when you move outside of research and development and maybe outside of software development as well. So Abzu will have to figure out where to apply rigidity and where to stick with the fluidity of self-organization the way it currently is. Again, it isn't different from an organism. There are bones in my body that are absolutely unflexible. They solve a certain part of what it needs to be a human, but there are other parts of the body that are extremely flexible, the immune system being the most extreme example. So we will mimic that as the organization grows. And there isn't a set formula. It's just something we have to keep an eye on.
And also in our body, we have parts that are like machine. Heart comes to mind, that must operate as a machine in a predictable, methodical way. Otherwise, we're done.
Otherwise, all the self-organizing neat structures in our brain and our immune system is pretty much done for. Yes, that's exactly true. Right? That's you can't think of a company either as a blurry mass of organic goo. There is structure there, but the structure depends on what you want it to do. So there's a conscious design that we in the organization will have to do as the organization develops. And I think we're in that phase right now, where we're moving into a much more commercially focused. So we're starting to walk on two legs here, not just inventing cool stuff, but also doing a more machinistic, machine-like approach to actually lead generating and selling it. And that requires different structures. But we will never be completely classical corporate. That just doesn't run in our vein.
Yeah, I wonder if any company that is being built today will ever become that old school corporate. We talk about how most things are like organic systems rather than machines in life. But then we can also see that machines are becoming less like machines because of artificial intelligence progress there. So the room for mechanical approaches seems to be shrinking quite rapidly.
I think I sometimes say all the road tracks have been laid. Right? The easy problems, the problems that can be solved on a conveyor belt have been solved. The remaining stuff are the things that cannot really be put into a manufacturing process like that. So we are becoming more and more in order to innovate and solve problems that haven't been solved before, I think we have to look more and more at organic and self-organizing systems. And of course, that just impacts the way I think. It's fascinating to think about how the ideas of the day tend to be connected in that way. Like there's if you think about what really there's a kind of meta ideas that just goes around across a lot of levels and arise at the same time. And currently, I think the idea of the organism is very much a meta idea across a lot of fields. A couple of years ago, I would say it was complexity and the idea of systems thinking. When Sigmund Freud invented psychology, the steam machine was the thing. So a lot of the metaphors in classical psychotherapy is based on steam engine metaphors. It's just the way we are, right? That we take ideas from one domain and apply it, and sometimes it's good, sometimes it's not. And I'm sure that the ideas that I'm currently completely consumed by, which is about self-organization and organic things, is also going to be limited. And then 100 years from now, people will say that he should have thought about that or that. But it'll certainly solve new kinds of problems.
In terms of your team building, when you're hiring new team members today, what do you look for? And when the candidate is clearly not a fit?
First of all, given our somewhat unique culture, we look a lot for self-motivation and drive. It requires a certain personality, I think, to thrive in Abzu. And it is about, sometimes people call what we're doing self-management. I'm not sure what to think about that word, because if you're managing yourself, are you managing anybody? But in another sense, we're all always managing ourselves. So I'm not sure what to think about the word itself. But what is true about the word is that we rely more at Abzu on you having self-discipline than a lot of other organizations do. So if you're good at motivating yourself to work on the right things, then you will find it easier to work at Abzu. And if you're more like, I like to do my thinking stuff at home, and then when I go to work, I would like to just be told what to do. And I don't actually want to be negative about that. I think I know a person who's a brilliant guy, but he's a renovation worker in his professional time, and he just drives a truck and picks up garbage. And you could say that's waste of his mental resources, but he applies them elsewhere in his private life, and it just pays him well. And he just wants to be told what route to drive and where to pick up garbage. And then when he comes home, he can do his creative thinking. That's perfectly fine. But if you are like that, you're not going to like it here. And that's just the way it is. So I look a lot for people who are entrepreneurial and self-motivated and disciplined in the way they work. So that's one side. The other side is emotional intelligence. We have to keep, this is not a rule set in stone, and we have a very interesting balance of young and more experienced and mature people. But what is really important is that if you are a mature and experienced person, then you must have taken that maturity in a direction where it involves. There's two ways. I think there's two ways that you can become mature. You can be a little disillusioned and say, "All right, I'm just going to tell you this is the way to do it, and I know better." Or you can be, in a way, beyond that and say that, all right, I understand the properties of youth, and experience is also quite often where the greatest ideas come from. So if you're taking that direction, your way of thinking about the reality as a mature person, then you fit in fine here. But if you're taking the other direction, I've seen it all, I've known it all, I don't want to listen to any more crap from people who don't know, and then it's hard to manage anything here. So when we look for senior people, we look for this EQ property. If you're a younger person, that's less important, because you tend to go with the flow. You join the company, and then you're treated with respect, and then gradually you build up your self-esteem, and hopefully you become one of these tolerant and open-minded people. But yes, I think the core idea on the EQ side is that when we look for experienced people with a lot of years in the industry, the emotional intelligence is what we look for more than anything other.
Did you have a case when you had someone who would have been a great fit from all the qualifications, but lack of that EQ led to your not being able to work together?
Yes, a lot of cases. Most of them, fortunately, in the pre-hiring phase, but it is something that that we've learned also the hard way in the inside of the organization. That yes, there are certain senior people who doesn't find it easy to work here.
Is it because of the current stage of Abzu that it's still in that more of a research stage? Do you expect to have more of those people when the Abzu grows and need that machine piece?
That's a very good question. And my gut is saying no, we need emotional intelligence. And above all, no matter where we go, machines or not. That would be my guess. But let's see what I think about that when we have a 100-strong sales organization sitting somewhere.
Yeah, that's another quite important quality of everyone who works in startups at early stages is being open-minded.
Yeah. I mean, I love learning. And one thing that if I should emphasize something that I like about the Danish culture that from which I come, it is really this: failure is not really a problem. We all mess up and we all do stupid things, and in a way, I don't even think about it as stupid. It's just learning. I cannot do anything if I don't allow myself to fail. So I'm not even ashamed about admitting. I've never shied back from admitting mistakes or stupidities or failures in my past, and I love learning from them. So in this case, yes, my organizational thinking is the product of where I am today, but it's different from what it was 2 years ago, and 2 years into the future it will be different from what it is now.
And being okay with failing and setbacks is also, I think, something that is quite important quality for everyone working at. You mentioned it, and someone I talked recently with, that's what he told me. His scientific career in academia taught him to be fine with failing. And he credited academia for that skill that he acquired and that now helps them to run their company.
So two things I really want to say here about it. One is, yes, and it requires specific cultural awareness to make sure that the acceptance and tolerance and actually celebration of failures remain part of your culture. And there's actually two things at play here. There's two types of behavior that I really try to address when I see it. One is if you are attacking a person for failures, and that's obvious, right? So if somebody attacks another person for their failures, and you're driving out creativity, just that's obvious. A less obvious thing that you also need to deal with is that there are some people who, even if their failures are addressed in a respectful and matter-of-factly way, still get defensive. And what they're doing is they're teaching other people to not help them learn. And that I think you need to react to just as strongly. Like these two behaviors, they're probably human, but these are two behaviors that we have to tackle if we want to keep a learning environment. Don't go after the person. Just give constructive, positive, but honest feedback about failures if you are the feedback giver. And on the feedback receiver, don't get defensive unless you're being attacked personally. But actually take it as the gift it really is. And it takes a while to get used to. I also still get defensive now and then when people highlight my failures, but I really shouldn't.
It does. It's a human nature on one hand, and it is also, from what I learned from behavioral psychology, it's also trained reaction that is trained when we are kids, and it's really hard to get rid of it. In a lot of sense, I'm not even sure we can do it ourselves. Maybe we need more than just, goodwill and trying hard to get rid of that. Maybe we all need professional training to get rid of it. We are totally fine with professional training in other areas. Why wouldn't we professionally train to overcome that reaction that we have both intrinsically and trained from the early years?
Yeah, I think that's a very good point. And actually, it's very interesting. I have 4 kids, so I'm thinking about how has the way they were brought up impacted their behavior towards this. I haven't thought about that before. I'll give that some thought. Maybe I should go home and test them, give them a little bit of constructive feedback and to measure their reaction.
It's a very interesting challenge to take on. Turning to the future now, what are your long-term goals for the company? What kind of new use cases you see for Qlatis in the future? And ultimately, what is the path to the general AI?
First of all, we talked a lot about System 1 and System 2 and how the reasoning layer is somehow intertwined with the estimation capabilities of the System 1 parts of our brain. And that is also part of what is in Abzu's future. So we're working on already now on connecting those two pieces and wrapping in the lawyer or interpreter style sense the Q lattice over other machine learning approaches that are better at rapid estimation. So we get a step closer to building something that mimics some of the core properties of the human brain. And that will allow us to incorporate, say, for instance, medical imaging, but also other image types of data and sequence types of data into our explanations, which is, of course, in its own important and can take us to new places and will make the Q lattice even more fully horizontally applicable. And that is also still staying on the relatively near term. What will happen next? We are spreading out and preparing to launch a new application based on the Q lattice that is intended to go much wider in the horizontal market. Yeah, the sales will be made public relatively soon around the year's end. But fundamentally, this is where we want to take the Q lattice and making it a widely applicable go-to solution for finding insights from data across ultimately all industries. So that's the near term, say, year-long plan from here. And that will, of course, also be compiled together with attacking some new verticals. We love life science and pharma and will stay here forever. But we would like to supplement that with a few new, maybe not as large additional verticals before we think about it as a fully horizontal approach. But ultimately, the goal is to be the fully horizontal AI-powered research and understanding augmentation system across any field where explanations and insights are needed. And this is the midterm goal. So in a couple of years, this is where we would really like to be the platform or system that you used when you were looking for insights from data, small or large, in any field. Somewhere around that time, a little after, the company itself should be ready for an IPO, actually. When we got together, the founders, back in 2017, when we agreed to do this company, we gave each other a musketeer's oath. We were not going to just sell this off to one of the tech giants. I've had other startup companies, and that has been fun, but I always exited early. Not of my free will in most of the cases, though, I must say. But I think there's a European defect, actually. I think European founders tend to exit early. And I just think that's part of why a lot of the real successes, the really successful companies in the US, at least the Western successful companies, of course, China is also a big player here. I would like to find the European path. I think we should be this tech giant out of Europe. And we are off on a good footing. We have a very transcontinental team. We have an office here in Copenhagen. We have one in Barcelona. We have a small one in Basel as well in Switzerland. And I would like to grow from there, not meaning that we won't ever also get a strong foothold in the US. That's actually next on our expansion plans. But with this European-rooted company. So that's part of what we see the company developing into. Along this route, of course, combining System 1 and System 2 and making a general purpose reasoning platform will eventually evolve towards something that some people would call artificial general intelligence. It's a little of a discredited term, rightfully so. I think 4 years ago, everybody was doing AGI and like nobody knew how. And I still don't think anybody knows how. And I don't think that Q lattice plus deep learning is all it takes, but it could be part of the piece. Could be part of the puzzle. And there's a deeper philosophical question here that I think is what motivated me to found this company in the first place, which is, what is intelligence or thinking or reasoning? Ultimately, what is the thinking subject actually? And I see that as my life's challenge. I really just want to get deeper and deeper into this. I'm not sure I'm ever going to be able to explain exactly why we experience this wonderful thing of the self, why there is this subject, why we seem to be apart from the world, although we are certainly a part of the world. And this entire philosophical conundrum of the hard problem of consciousness, it's like I think we will get closer. And I think I could play I and and this company could play a part in getting closer to understanding these questions. So that's certainly part of what I want to use Abzu as a vehicle for exploring. At the same time, that also raises a lot of interesting philosophical questions and ethical questions about what we should and should not do and what we should and should not work on. And that's an interesting balance in its own right to have to walk. Right now, I think it's hyped. Like most of the talk about machines reaching self-awareness and stuff like that is just people trying to get airtime. There's a long way from the neural networks of today to any kind of actual conscious thought. But that doesn't mean that we won't ever get there. So it is most likely questions that I'll have to deal with, that all of us will have to think about in our lifetimes.
There is a lot to expect in terms of positive things from the development of AI, and of course, a lot of things to worry about. And in terms of what you mentioned about understanding how our thinking works and consciousness, I don't know about consciousness. Consciousness isn't such an elusive thing. But in terms of understanding our brain, I think studying the machine learning approaches did teach me a lot about the way my mind works.
Yeah, I think that that is absolutely true, and that's why I'm in artificial intelligence. But I also think that you put your finger on the problem here. I think that that studying artificial intelligence is studying what it means to be a thinking entity from the outside. So we're continuously thinking, reducing problem of being to an observable set of properties that we can observe from the outside. Although we instinctively all know that the true meaning of being is actually subjective. It's actually something that's inside of us, and it cannot be studied from the outside. No matter how hard, you can only see the behavioral artifacts that are a consequence of me being me. The only one who can really observe me being me is actually me. And that also goes for machine learning. We can never really get inside of the systems. And I think it requires, at some point, it will require a new scientific framework to even start thinking about what a system looks like from the inside of itself. There's a British philosopher called Philip Goff, who comes from the panpsychology style of thinking, who wrote a book called Newton's Error, which I really like that book. I'd actually recommend it to any reader interested in these questions. But I think what he really zooms in on is that the way we do the scientific method, the way the science is done, is designed to rule out intrinsic properties of anything. So we're only studying extrinsic properties. And of course, that will never tell us anything about the intrinsic properties because we're purposefully ruling them out. So he doesn't suggest a new scientific framework to deal with it, but I think he correctly points to the problem.
This is a very interesting idea. I'll definitely link the book in the show notes for everyone interested to read it. Casper, thank you for joining me today. It was great talking to you.
Thank you. Thank you for inviting me. It's been a great conversation.
Thank you for listening. You can learn more about Abzu on their website and follow Casper on Twitter. The links will be in the show notes.